So, welcome folks of probabilistic robotics, waiting for the critical mass to assemble. One. Three, 4, 5, 6, 6. We are at 6, 5. Come on. Anyway, let's start the lesson. So the lesson of today will be divided in two parts. There will be one part that is theory, and it will be about the Unscented Transform and Unscented Kalman filter. And then we will have a practical with Tiziano from home, where we will have first a YouTube session, and then we will switch to Meet so that we will assist you in doing the exercises. I did not have time to edit the videos of the practical, but I made them available in the integral version on the web page. I think you all received access to a shared folder on Google Drive. Should you have any problems to access, please let me know, because probably I made some mistake with the permissions. Now, the lesson of today will be about the unscented Kalman filter. And unscented means unsmelly. And then we will introduce this new concept, and then follow the derivation. Follow the derivation of the generic filter after having defined how to perform the basic operations on this new representation that we will of a probability distribution that we will discuss. And I invite you at the end of today to implement the systems that you have already seen in the exercises by using this new paradigm of filter that we will teach now, because it will require only minor modifications to the exercises that we have presented. Okay, now what is the unscented transform? As usual, now switch scheme. As usual, in the slides, I have to put the recap, but let's assume that the next time you will pull, you will find the syllabus of the lecture in the first slide. The unscented transform is a way, an alternative way to parameterize a Gaussian distribution. Now, at this point of the course, you should be aware of the equation that describes the probability density of the Gaussian that is reported in this slide for completeness. Now, once again, I'm going to repeat that the parameters of a Gaussian distribution in the momentum parameterization are a mean and a covariance matrix, sigma. And these numbers uniquely characterize the shape of a Gaussian distribution. Okay? Alternatively, you could use the information vector and information matrix, which is which can be easily determined from the covariance matrix and the mean. Okay. Now, So these are the parameters, mean and covariance, or information vector and information matrix of a Gaussian shape, no? All of a Gaussian distribution. Alternatively, we could represent it in a different way, as a set of samples. A sample is nothing else than a value in the space where the Gaussian lives, right? So if the Gaussian is a Gaussian on R3, a sample will be a point of R3. And in addition to this sample, we attach to it a weight. Now, if you remember, when we have seen the Gaussian distribution, we have seen how to estimate Gaussian parameters from a set of samples of the distribution, that were obtaining the mean by averaging all of them and obtaining the covariance by averaging the outer product of the difference between each sample, of the sum of the differences between each sample and the mean. Okay? And, well, if I give you a gazillion of samples, and you operate with these samples as if they were the parameters of the distribution, you could still represent this distribution by using these samples that you could imagine as if they were control points of your distribution. So you put the samples more far away from each other, and then accordingly you will have a larger shape of the covariance matrix, the magnitude of the covariance matrix will increase, and so the bell will be flatter and wider. Okay? Anyway, instead of using a million of samples, the unscented transform uses a deterministic number, so that numbers, which depends on the dimension of the Gaussian, of these samples, these points, in the state space of the, or in the space of the distribution, right? So if I have a three-dimensional Gaussian, I will have a certain number, which depends on the dimension of the Gaussian, of these control points, which are selected deterministically into the sample space, and their position will influence clearly the shape of the Gaussian itself, because if I shift all these samples to the left, then I will also, this will result in shifting the mean to the left, or similar operations. Then these are samples, and attached to these samples I can also put some weight that will scale basically each of these samples based on its importance, in a way that the heavier a control point will be, the more the mean will lean towards that point. Imagine that this point here has a weight 100 and these points here have weight 1. Well, I might expect that the mean will more or less be leaning towards this point. Instead, if all points have, well, in this case I selected the points to be 1 exactly in the mean, but imagine that you have them randomly put. If I increase the weight, if this point here will have value 100 and all other points will have value 1, right, I might expect that the mean of this distribution will shift toward this point over here, right? Okay, this is more or less how we can represent a distribution with a set of points or samples or control points in case of unscented transform. Why control? Because they are selected deterministically, they are not randomly selected deterministically based on the parameters of the Gaussian, which is the covariance matrix and mean. Okay, now what we will now talk about is how to determine the sigma points and the weights. So these points in the unscented transform are called sigma points. One sample with a weight is called a sigma point. Okay? And it's characterized basically by a position in the state of the distribution and a weight. Okay? And we will now define, now if I tell you how to switch from covariance matrix and mean to a set of sigma points, and I tell you how to do the opposite operation, to start from a set of sigma points and recover the covariance matrix and the mean, if I explain you these two operations, basically I have qualified the domain, because you can always go to one representation, do what you have to do, and go back to the other representation. And it's obvious that in selecting these samples deterministically from the shape of a covariance matrix, of a Gaussian distribution, I will have to ensure that these two operations are consistent, which means that if I start from a Gaussian distribution which has a certain mean, a certain covariance matrix, and then I compute the sigma points, and then I go back. So from the sigma points, I want to recover the covariance matrix and the mean. Then I should get the very same mean from where I started. Otherwise, I'm gonna make some mistake. And so we will talk about these two directions. Like from a covariance matrix and a mean, we obtain a set of sigma points, which we will call two unscented, and another function that, starting from the sigma points, recovers the mean and the covariance matrix. First of all, let's see in detail what are these sigma points. Okay, a sigma point is you can imagine it as if it was a data structure, no? A struct, a set of things. One sigma point is one sample, right? Is one sample which is, like, for sure I need to have a sample. And the sample is just a vector in the space of the Gaussian distribution. So if the Gaussian distribution has dimension 3, then these samples will be an element of R3. If the Gaussian has dimension 20, this sample will have, this value will have dimension 20. This I denotes the number of the sigma points, because we have a certain number, sum of them. Okay, and this basically, if you want to look at the image or at the picture, this is basically the position where each of these points lies. So this will be one sigma point, this will be one sigma point, and so on. Then, instead of having one single weight, for some obscure reason, we have two different weights. One weight which is used to recover the mean, and one weight which is used to recover the covariance. So for each sample, I have two scalar values. One weight that I call Wm, that I might imagine as pet as the point, and one weight that I call Wc. And this will be the way that I will use when I reconstruct the covariance matrix, or the mean from that point, and this will be the way that I use when I reconstruct the covariance matrix for that point. And let's call a single sigma point with this mathcal letter, x with I. This is one single sigma point. This is the data structure with these things. Now, how can we reconstruct the mean from a set of sigma points? Well, quite straightforward. The mean, mu, will be computed as the sum, the scaled sum of all the values of the points, which means the position of the sample, scaled by the weight that we use to construct the mean, Wm, right? Very similar to the definition or to the construction of a covariance of a mean from a set of samples. And similarly, when we want to construct the covariance matrix, which we can construct after having computed the mean, well, the covariance matrix will have this form. It will be nothing else than the sum, the scaled sum of the outer products of the difference between the position of the point and the mean computed at the previous step, well, the outer product, which returns us a matrix. Each of them, each of these contribution will be scaled by a coefficient Wc, which is attached to the sample, to the particular point. Okay, it's very similar to the mean and covariance matrix that you have that you use when you want to recover the parameters from the samples. Let me see if there are questions. No. Tiziano, please answer the questions should they appear in the chat, because I might lose them during the lesson. If the unique student in the lecture hall has questions, please ask them. Right? I assume your questions will be representative for the questions of those at home. All right. Now, basically with this slide we have defined this operation over here from unscented, right? So I give you a set of sigma points, each characterized by a set of positions and a set of weights, so each characterized by a position and a weight, and then you recover mu and sigma. We defined how to go from here to here. Now we need to define how to go from mean and covariance matrix to sigma points. How do we do? Well, some way we have to do. So let me recap for those of you that has never seen the Cholesky decomposition. Well, the Cholesky decomposition is yet another decomposition of a matrix that must be symmetric and positive definite. And basically, if a matrix is symmetric and positive definite, then we can find the two matrices, or one matrix L, that multiplied by its transposed, triangular, lower triangular matrix, that multiplied by its transposed, which being this transpose becomes an upper triangular matrix, is equal to this, is equal to A. Okay, this is the definition of a Cholesky decomposition. So, the Cholesky decomposition of a matrix is a matrix that, of a matrix A, is a lower triangular matrix L that, if multiplied by its transposed, returns my original matrix A that I want to decompose. And it's more or less the analogous of the square root. So if A was a scalar, the Cholesky decomposition of this scalar would be just the square root of this scalar, because you take a scalar and there's only one, if it's positive, there's only one number that multiplied by this number returns, get multiplied by itself returns the original number, which is basically the square root. Okay? It can be computed straightforwardly by using a variant of Gaussian elimination, the Cholesky decomposition. In MATLAB, you can calculate the Cholesky decomposition, or in Octa, you can calculate the Cholesky decomposition of a matrix by using the function CHOL, C-H-O-L. Okay? If you are interested on how to compute the Cholesky decomposition, you can wiki. You can also write, implement a very straightforward algorithm that it's a variant of Gaussian elimination that can be used to compute the Cholesky decomposition. Okay. If you want, I will put a small C snippet of code in your repository in case you want to have a look at how to compute it. Hence, one thing should stem out from the definition of Cholesky decomposition is that the matrix must be symmetric positive, because if the matrix is not symmetric positive, then we cannot find if it's negative. If it's negative, it might be that no, it is actually that this L will have imaginary values, right? And so we are out of the real domain where we try to stay. Now, having said that, given an SPD matrix, which basically is symmetric positive definite matrix, you can compute its Cholesky decomposition. Now, why did you talk about the Cholesky decomposition? Because it's something that I need to describe you the procedure to determine the sigma points. Okay, now, let's call the Cholesky decomposition of A, which is this lower triangular matrix here, L, and let's, like, with an abuse of notation, define it as the square root of A. Okay? Now, if I take a matrix A, and with this notation here, A in brackets I just denote the ith column vector of this matrix. So this will be AI with 0, this will be AI with 1, AI with 2, AI with 3. So with AI, I just denote the ith column of a matrix. Okay? Then let's, if I compute the Cholesky decomposition of A, then I obtain the square root of A, and I can similarly determine the, talk about the eth column vector of this decomposition. Okay? Okay, this is the classical exercise that I give to those that want to get in touch with the Cholesky decomposition and see how to determine it, how to compute it, and just implement in C, C++. It's, I think, quite funny. All right, now I talked to you about the Cholesky decomposition of a matrix, and you already guessed that I will have to compute somehow the Cholesky decomposition of a symmetric positive matrix, which will be the covariance matrix, because otherwise I wouldn't have talked about the Cholesky decomposition, at least not at this stage of the course. But then there is an aspect that we have to consider, which is the dimensionality of my representation. Okay? When I move, how many free parameters do I have in the mean and in the covariance matrix? Well, for a Gaussian of dimension n, I have n parameters, free parameters for the mean, and then I have n times n minus n plus 1 times n divided by 2 parameters for the covariance matrix, because we know that the covariance matrix has to be symmetric in addition to be positive definite. And so the number of free parameters is only the parameters that I have in the upper triangular block, right? Now, if I have a set of control points, and how many control points would you choose to represent this Gaussian? It's kind of weird, because you should choose the least number of control points in order to preserve the same, not to gain degrees of freedom. But if you don't gain degrees of freedom, then basically, then stay with the covariance matrix and the mean, because then basically the two representations are completely equivalent. What we would like to have with the unscented transform is to gain some flexibility in manipulating the Gaussians. And so the mathematicians decided that for a Gaussian of dimension n, you will need 2n plus 1 control points. And given that each control point basically, ignoring the weight factor, gives you n degrees of freedom, where n is the size of the Gaussian, well, then you clearly have many more parameters, because you have two n squared plus n parameters in this case to represent your Gaussian. Because if you have 2n sigma points, 2n control points, this is the number of points. Each point has n degrees of freedom, which are those contained in the sample vector in x, just to understand. Then you have 2n squared free parameters plus n, because there's 2n plus 1 control points. Okay? And you have a lot of them. And so you basically have a million of ways, like you have a clearly redundant parameter space, and then the question is like, where do I choose my control points? Just like to visualize why this looks this way, imagine that you have a Gaussian that looks like this. Okay? Now, a naive idea would be to extract these control points, one at the mean, and the other control points along the axis of this ellipsoid, along the axis of the covariance matrix, right? So one, I put it here, and the other one I put here, 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 and here, right, along this axis. Now, when I want to recover the mean, right, consider also that I have the weights as a knob in my system. When I want to recover the covariance matrix, I could represent the very same Gaussian by choosing points which are closer basically to the mean and have a low weight, or by and they have a high weight, or by choosing points which are further from the mean and have low weight, or vice versa. But I can just like put points which are further, decrease their importance, or put points that are closer and increase, put points that are further and increase their importance, or put points that are closer to the mean and decrease their importance. Okay? This would be a way to represent I have three parameters basically to define it. So I need to find a way to choose basically a set of valid weights having defined how to place these sigma points. So I give you these sigma points, you put them on a table or in a region, and then I ask you, okay, given these sigma points, find me some weights that will make these sigma points representing exactly that Gaussian distribution. You can imagine it this way. Then I change a little bit the layout of the sigma points, and by playing with the weights, you can decide to represent the same distribution because I moved the points. Okay? You have also the degree of freedom of the weights in the game. Now, a reasonable way to talk about the sigma points, because it's very visual, is to determine the sigma points along the axis of the Gaussian. But doing so would require to calculate, if you remember, the eigenvalue decomposition of a Gaussian of a covariance matrix, which, imagine that you have a covariance matrix 1000 by 1000, might be a very, very expensive option. So you don't want to do this. You have to find another way, which is faster, that allows you to extract or to determine the position of these points. Hence, we introduce the Cholesky decomposition. Okay? Now, clearly the weights and the position of the sigma points are correlated, because if I change the weight, I will also have to change, and you already spotted it, the magnitude, the position of the point along the direction that I choose for sampling from the mean. Changing the weight will result in picking a point, maybe along the same direction. Now imagine that these sigma points, these samples are drawn along the eigenvectors of this matrix. Then if I change it, then I might move it or either closer or further to represent the very same portion. Now, it's not the aim of this particular. If you're interested in the unscented transform, there is a paper of Julier et al. You can wiki actually for unscented transform and find a lot of things. Here we want to have just an operational way on how to calculate the sigma points and then derive our filter. Then there is some black magic that the mathematicians have done, and then they have defined the three parameters that determine how to select, how to choose these sigma points, given that we have selected a set of directions where to sample them from. And these are k, alpha, and beta. How to select those? Well, in general, there's a lot of dissertation on how to, depending on the characteristic of the process, depending on a lot of things. In the end, I just restrict myself to use these parameters for determining the Gaussians. Like, what are these parameters? You will see it in the next slide. It's three real numbers that determine the influence, how the sigma points will be drawn. Just use these three parameters. And the important thing is that once you go forward and back by using the formula that I have described in the previous slide, in the 2 slides ago, if you go from here to here and back, then you need to get the same covariance matrix. Once you move from here to here, you will have a bloating of the parameter space, but this bloating in the parameter space should be destroyed once you go back. Okay? Now, having said that there are these three magic numbers, now finally I can tell you how to determine, how to calculate the unscented transform, or the sigma points from a Gaussian distribution. How? if n is the dimension, as I anticipated, we will have 2n plus 1 sigma points. The very first thing that you have to do is to compute these quantities. One quantity which is called lambda, which is a number that depends on the dimension of your n is the dimension of the Gaussian, and depends clearly on the parameter alpha that I was talking about before. Then you extract the Cholesky decomposition of the matrix A multiplied by this famous n plus lambda. This will be, or clearly you could also extract the Cholesky decomposition of A and multiply this matrix by the square root of n plus lambda, which will be completely equivalent. This basically gives you a lower triangular matrix. A lower triangular matrix of vectors. And these vectors denote the displacement in the space of the Gaussian, where you have to draw the sigma point. So you stuck into the mean, which will be actually the very first sigma point. And then for each column of this matrix over here, for each column of the Cholesky decomposition of this triangular matrix, you draw 2 sigma points, one positive and one, let's say, negative, by simply taking the mean and summing to this to the mean the vector of L, which corresponds to the ith component. So you have the mean, and then basically for all the sigma points between 1 and n, let's say this way, you take the mean and you sum to this mean the first column, the second column, the third column, the fourth column, and then this way you generate the first n sigma points. And then you do the opposite operation. You take the mean and then you subtract the other vector. So it's like picking a point on the one direction and picking a point on the other direction. The order of the sigma points doesn't matter, because the order is destroyed by the sum operation that we do later on. Okay? And normally in an implementation, you sample positive, negative, because it's smarter than doing before first all the positive and then all the negative. Or, I mean, for me it's more natural. And this basically tells us how to determine what? How to determine one important part of the sigma point, which is where the point lives. No? Where is the sample? Basically, with this operation, we extract the location of these points that, just to show visually, we define a first sigma point which will be on the mean, then assuming that this vector over here, vector that goes from here to here, will be the first column of the Cholesky decomposition, then we sample a point in this location and in this location. No? Because one is the positive direction and the other one is the negative direction. Okay? And then we sample a point, we take the second direction, and we sample a point in the plus and in the minus of this column. Okay? So far, so good. And then what about the weights? So we define for each sigma point the index, and then, all the locations. And then what do we do about the weights? Well, this is the mathematician said that the weights have to be this, right? So, given the parameters alpha, beta, and kappa that we defined before, Wm, the weight of the first sigma point, so the sigma point of the mean, is the only one that has different numbers for the weights, right? And these are the formulas that I'm not going to comment. Lambda divided n plus lambda, and so on. Where lambda and n are completely defined based on the previous slides. Okay? As an exercise, you could simply take these slides and try to implement a small program that, given a covariance matrix and a mean, extracts the sigma points and goes back, right? And this will give you, but there's no need to debug, because this will give you automatically or this will help you to debug, because the debug is the program itself. If you go from A to B and from B to A, and then you come back to the same point, you might, for multiple covariance matrices and multiple means, you might assume that your calculation is correct. Okay? And you might also have fun in changing the parameters and seeing what happens. Okay. Now, all this story and all this introduction was aimed at introducing basically a new way to parameterize a Gaussian distribution. And what do we do? Why did you have to do this if we were so happy with the covariance matrix and with the mean, or with the information vector and the information matrix? Well, because having this new parameterization results in having simpler operations when we work on the Gaussian. Now, the big evil, one of the big evil, or the only aspect that we have to compute, like with a pen and paper so far, is the calculation of the Jacobians when we have to work with a Kalman filter or with a like Kalman filter so far. And this might be error prone if you do it by hand. Okay, there are symbolic calculation packages, there's the impossible around, but let's restrict on the pen and paper for now. And so, like, you might want to get rid of these Jacobians, and this is basically what the Unscented Transform will let you do. Jacobians, I recall you that the Jacobians are only used when we deal with nonlinear functions. Because if the functions are linear, the Jacobian is basically a coefficient matrix of the function itself. All right, now, all said, now let's see how we can define our funky manipulations, probability density manipulations, on this new parameterization. The same as we have done for the Gaussian distribution. How to marginalize, how to condition, and so on and so forth. All right, the very first operation. Unscented marginalization. So let's imagine that we have a random variable xt, which is composed by two blocks, one block xa and the other block xb. We represent this random variable through a set of sigma points that I call here ut, like Unscented Transform, of these are the sigma points and these are the weights, right? Now, the marginal distribution, if I want to marginalize out xb, which basically means integrating over all possible xb, then I could straightforwardly obtain the unscented approximation, which will be a set of sigma points that represent the marginal distribution, so P of xa, in an unscented as a set of sample points. How would you do it? Remember what we were telling about what happens when you marginalize a distribution. Basically, you collapse a variable that you're not interested in, right? This is just a consequence of that, this operation, because basically this means that you have to take each of these sigma points, each of them, and then you have to suppress, imagine that this is xb and this is xa. And you have to suppress the xb components from the sample, this way. Or this was xa, sorry, this is xa, this is xa. You have to suppress this is xb, this is xa. You have to suppress the xb components from the sample, right? Of course, you will find you have a dimensionality reduction, so you will find more points, more sigma points than you have to minimally represent this distribution. Imagine in this case you have a distribution that we started from a two-dimensional distribution here, and so accordingly we needed 5 sigma points, 1 for the mean and 2 for each dimension. Once we do the marginalization, we do it simply by suppressing one of the dimensions, the dimension of the variable of the block that we're going to suppress from the original sigma points, and this will result that all these samples here will be splattered along the axis of the surviving variable, or the surviving subspace. Okay? And so, well, we end up having more sigma points than what we need. Is this a problem? No. We have more sigma points, we carry on the calculation with more sigma points. At any point in time, we could also reduce their number by simply projecting them in the covariance and mean and coming back, and then we will have minimized the number of sigma points. But so far, it's not a drama, it's not an issue. Okay? No. Very good. All right. Marginalization was easy. I think, like also intuitive. I have one dimension, I have a set of samples. Well, I kick away the dimension I don't need from this set of samples, and I obtain the very same samples, but just splattered, projected in the same part of the space that survives the marginalization. Okay, that was easy. And another operation that we used to do is to take a distribution, right, and to use it as an input of a generic function in order to obtain another distribution, which is the projection of the original distribution through that function. So let's say that we have a random variable xa, which is described as the unscented transform, which basically is a set of sigma points. And let's say that we have a random variable xb that is obtained by applying a function f to the original, to the random variable xa. Okay? This is just a transform function that, given a point of xa, returns you a point in xb. Now, if I consider xa as a random variable, then also this one will become a random variable. And how can I calculate, basically, the parameters of this new random variable? Well, assuming, as always, hammering in the hypothesis that if I am in an unscented world, I stay in an unscented world. If I am in a Gaussian world, I stay in a Gaussian world. Well, the straightforward operation on how to determine the shape of this distribution, consider that you have a set of samples, right? You take each individual sample and you apply to this sample the function, and you see where it ends up. You do it for another sample and you see where it ends up, and so on and so forth, for each of these samples. So, let this be the input distribution, you apply this fantastic function, and this function might teleport your point, your x, from here to here. And this will be basically what we call xb with I, which is the projection of this eth sample of the eth sigma point. And you do this operation for all others. At the end of this operation, you will have what? You will have a set of sigma points. Where will these sigma points live? Well, in the space where you projected the original sigma points, right? Well, but I have sigma points. And if I have sigma points, I already have an unscented representation of that distribution. Okay? Clear? Cool, eh? F can be nonlinear in this case. There were no assumptions on F. It's not that this is correct, because it's not that this is always correct. It's always correct if we think about samples. But what we will end up and the position of the sigma points after the projection, they are not guaranteed to still represent a Gaussian distribution, right? Because this function can be anything, right? And points which were, if these points were originally the mean and one was on this side and the other one was on this side, which means basically that they were the distance between this sigma point, and this was equal to the distance between this and this, right? After the projection, this is not guaranteed, which might mean that some sigma points might be closer to the mean, or others, they can move arbitrarily. And then, once you recover the covariance matrix, you will get an approximation of the covariance matrix, of the covariance matrix after the projection. But this is nothing else than what we were doing when we were linearizing a nonlinear function. And in case the function f is an affine transform, then the unscented transformation is completely equivalent. This operation here will return you points that are guaranteed to represent a proper Gaussian distribution. So you don't have a loss.
The weights are preserved.
The weights are preserved. Your colleague in the lecture hall says, what happens to the weights? The weights are preserved because the weights, imagine that the weights are the amount of probability mass that is attached to the input point. So if I take this amount of probability mass and I throw it into another space, well, the probability mass stays attached to the event, which is actually the point. Because the more likely it is that I started from here, if starting from here I will end up there, well, the more likely it is that I will end up there. All right. Now, so marginalization was trivial, I guess, but it was as trivial as doing the marginalization in the covariance space, basically, which is consisting of suppressing a piece of the mean and a piece of the covariance. So it's quite symmetric. The functions we have seen. Now, let's talk about the chain rule. Now, imagine that we live in this funky unscented world. And the chain rule is defined by having a random variable xa, which is described once again as an unscented transform. Okay? Because that's what we're talking about today. Now, if I have a conditional distribution over a variable xb, which is characterized by a moving mean, which is a function of the controlling parameter xa, and the constant covariance, which I called sigma b of given a, sigma of b given a, then I would like to compute the joint distribution, p of xa and b, and in this case, let's say this way, that I want to compute it in covariance form, so with mean and coefficient vector. We could do this also with the unscented, in the unscented version, but for now, let's recover just the parameters of the joint distribution, okay? Because it will be handy in the derivation of the unscented Kalman field. Now, it's quite reasonable that the joint distribution the mean of the joint distribution will be consisting of a vector composed by two blocks. The first block will be the mean of this distribution over here, so the mean of xa. And the second block will be similar to what happened in the linearization of the, so in the affine transform, will be nothing else than the projection through f of the mean of this distribution over here. Because if I take the mean of this distribution and I shuffle it into the f, I will get another vector that is the vector in the space xb, and this is defined to be the mean. So the most likely point of this distribution will be also the most likely point of this conditional distribution. Okay? And so the mean becomes f of mu a, where mu a is the mean of this. And I'm happy with the mean. And then I will say, okay, the covariance matrix will have the following form. This is quite obvious because it will have the following form because it's just a form, it's just a partitioning that I do on the Gaussian distribution. It's just a way of giving names to this block, to this block, to this block, to this block. And also, I know that the covariance matrix of the inner noise of the conditional distribution, sigma b given a, will have to be added to the generic block, to the lower block. Because if I have no uncertainty here, all the uncertainty of this covariance, of this joint distribution that is concerning the xb over xb depends on the uncertainty which is projected through xa. Okay, so now this somehow we can recover because this will be nothing else than the covariance matrix extracted from the sigma points over the variable xa. This we don't know how much, we don't know much, and this also we don't know much. But now, let me make you guessing, like having an intuition on what we could do. We have an unscented distribution here, right? So we have a set of sigma points. What happens if we take each of these sigma points of the x? We take this point and we project it through f, which is the function that is moving the mean of my conditional distribution. What will happen is that we obtain a p, and we have this tiny vector which we will call xbi. Then we take the input vector and the output vector and we chain them. We put them one and then the other one on the bottom, just having xb, xa, and xb without. Okay? And this will become a new sigma points of higher dimensions. Okay? Now, if I have this sigma point of higher dimensions, and I can simply recalculate the covariance matrix as I was doing before, like just having a new set of higher dimension sigma points. Okay? This is the principle. It basically will be the sum of the outer products of the augmented sigma points. And this is exactly what happens, actually. So, we could simply say that sigma of A given B will be nothing else than of A given B is this block over here. So A and B, not A given. Sigma of A and B is just this block over here. Remember that this block is as tall as XA and as wide as XB. So then this will be the outer product of the difference between the mean of XA and the sigma point XA and the mean of XB and the sigma point XB. Now, how to remember this? You have just to consider that you take a sigma point of the input distribution, you project it through the function that is moving the mean in the conditional, you obtain an augmented sigma point, and then out of this constellation of augmented sigma points, you reconstruct the covariance. And this is nothing else than the restriction of the reconstruction of the covariance to the component of the vectors that are living in this region over here. If you will write down what I'm saying, so you construct the input vector, you construct the input sample, or the input sigma point. You augment it with its projection, which will be f of xa. So you have a larger dimension sigma point, and then you put them aside. You say, these are my sigma points. Each of them preserves its weight. Then after doing that, you say, okay, now I want to reconstruct the covariance matrix. Okay? You develop the summations, and you will find out exactly. And then, after having done that, you group the summation, you will find out exactly these two formulas. Where this formula here tells you how to recover the cross covariance, basically, between the XA and XB. And this is in general not square. And this is how to determine the covariance matrix, the covariance component of XB, to which we did not yet add the intrinsic noise, the intrinsic error, which was injected by sigma of B given A. Okay? And then now it might also be, it might also jump to your mind why I did not calculate, I did not say the output of this procedure is not a valid unscented transform. It's not a valid unscented thing. Because I do not have enough points, right? Once I do this operation, I start with a set of sigma points, which are my sigma points in XA, right? And they are a number which depends on the dimension of XA. When I apply the chain rule, I take these sigma points, and then I project them and I obtain augmented size sigma points, which are, so they have a higher dimension, and therefore they represent a distribution in a higher dimensional space. But they might not be enough, because if before I was working, for instance, with a distribution of size 2, therefore I needed 5 sigma points. Then I do a projection, like I do the chain rule, and in another space of dimension 2, then I end up with a space of dimension 4, for which I will need 4 by 4 times 2, like which is already 32 plus 1 sigma points. Right? But I still have, I started from 5, it's not that I can have more. Therefore, in doing this operation, you also go back to the minimal representation. Okay? And then this is quite interesting, because you can imagine it as augmenting the sigma points with the element which is coming from the projection, and then reconstructing the covariance, as you were doing. But remember that you will have to add the intrinsic noise, the intrinsic covariance of the conditional distribution sigma of B given A. Clear? Very good. So, like, this is how to do it. I have my sigma points. I take each of these sigma points here. I project it through F, and I obtain the tiny little sigma point in the other space, in XB, and I obtain XB with I. Then I can recover the mean over the projected space XB. And to do this, I just take the sum, or the scaled sum of all the projected points, and then I can determine the cross correlations by using this formula over here. XB with I is just the projection of the point XA with I through F. Okay, now we are able to do the chain rule, and now we need to do the conditioning, right? And then, having defined the conditioning, we can plug in this very same operations into our generic filter derivation and obtain a new filter, which we will call the unscented Kalman filter. That's one thing that we cannot do with the sigma points, is conditioning. Because if we have sigma points, we do not have a continuous distribution, right? And slicing sigma points that doesn't really work. So once we want to do the conditioning with the unscented transform, we don't do the conditioning with the unscented transform. We just go back to a Gaussian distribution in the canonical parameters, we do our conditioning, and then if we need, we go back to unscented again. Clear? To the Unix student, is it clear? Yes. It's good to have at least one representative of you in the classroom from time to time. Makes me feeling less lonely. All right. Now, let's go back to the filtering implant. Now, we have a system with Gaussian noise. It's not a mystery. We have seen it, I mean, up to the nausea, I think, up to this point. But we will see more, so that the nausea will increase. This is the classical model of a system with Gaussian noise. Now, we have our classical system with a transition function f. We have a control that is characterized by a distribution, so by a mean plus an unknown noise nu. Or we can also say that here in input you have already a distribution, and this is our transition function. I'm not going to waste much more time on it because we have seen it a million times. It's just the very same that we have seen for the Kalman filter or the unscented Kalman filter. Only that this function here is a generic nonlinear function. We have our fantastic generic prediction function, and then to the ideal prediction we have an intrinsic noise of the measurement function, and to the measurement function, to the output of the measurement function, you add white noise nz to obtain another random variable, which is our observed output, right? We know the process noise or the control noise, which we would call NU, and we say that it's zero mean Gaussian distributed. We know the measurement noise NZ, and we say that it's zero mean Gaussian distributed. And we also assume that we know the initial distribution of the state P of x0, which is distributed according to a mean mu0 and a covariance sigma 0. Okay, no? I made churchy voice. And then we talk about the control as a random variable, because this was deterministic as a random variable, which is centered in a random Gaussian variable centered in mu u t minus 1 with the covariance matrix sigma u at time t. T minus 1, this should be. There's a mistake here. Sigma u t minus 1, to be fixed, not to self. Tiziano, write it down if you're listening, but probably you're not. All right, so now, this is our model, and now, having said this universe of things, and all this derivation on the unscented Kalman filter, on the unscented transform and unscented representation of a Gaussian, let's construct now our filter that will operate on Gaussian distribution represented as unscented points. Okay? Remember that in order to calculate the chain rule, we did not need to calculate any Jacobian, even if the function was not linear, right? So we will preserve this property in the implementation of our filter, in the derivation of our filter. That's one thing to be said about the unscented transform. Well, the fact that you have the unscented transform is completely equivalent to the normal Gaussian parameterization if the system is linear. So you don't lose anything, and you probably gain also some computation if the system is linear. But if the system is nonlinear, having more degrees of freedom lets you represent better the nonlinear effects. And so it's able to actually approximate the evolution of the system up to the second order instead of up to the first order. Okay, so if the system is highly nonlinear and there is some effect, you might want to use the unscented transform. And we can use the very same mechanism that we have used for the derivation of the Kalman filter. The only thing that we will have to do is to represent to calculate the predict step by using the unscented function projection. Right? You have the function f. If you have a distribution which is represented as a set of unscented points, you take all these unscented points, which are consisting of a block that is the x and a block which is the u. You take each of these points and you throw it into f, and you will get a new set of sigma points. Perfectly legit, perfectly nice, which will represent the next state distribution. At this point, you have a sigma point. You have a transition observation function. And so you can determine the conditional distribution of the measurement given the state. And so you take these sigma points of the predict and you shuffle them through the prediction to the observation function, assuming that the prediction will have a constant error sigma z given x, right? Which is constant, it doesn't depend on the state. And then you will get the chain rule. And then after you have the chain rule, you will obtain you will perform condition. You will have P of Z and X. After having P of Z and X, you take the actual measurement, you condition on the measurement on this distribution, and you get the update step of the filter. Clear? Let's see operationally how to do it. The predict. Remember, the role of the predict is to incorporate the control by computing the Gaussian distribution of the next state given the input. The ingredients are the transition function, f of xt minus 1 ut minus 1. We know that the previous state and controls are distributed according to a generic distribution. Let's say that it's a Gaussian, because after conditioning, we will always have a Gaussian distribution which is represented with mu and sigma. because conditioning cannot be done in the unscented space. So we are doing predict, and so which means that we come out of an update at the previous step. So our input distribution will be a distribution, let's consider the joint distribution over previous state and previous control, which will have the following shape. We have already seen it in deriving Kalman. What do you do to apply the transition of a function? What would you do? Unique student, what would you do? I want to use the unscented transform. I have this.
We use the mapping we saw before. To go to
exactly. Exactly. So the unique student set, we use what we have seen before, the mapping that we have seen before. We have this Gaussian distribution and we obtain a funky family of sigma points. Right? Remember that these sigma points have to be drawn in the joint distribution of x and u, right? No? In all of it. But actually the Cholesky decomposition of this and the Cholesky decomposition of this are decoupled, right? So, but we will have the sigma points of dimension x plus dimension u, right? Then we take these sigma points and happily we throw it, all of them, through f. Remember that throwing a sigma point through f doesn't change the weights, only change its position. And I have a family of happy sigma points which are living in the next state. Right? And this way I obtain from this sigma point xt given t minus 1 without that I have drawn before. Remember this abuse of notation that you have dimension x plus dimension u. I will get a new family of sigma points that will be, as I said, happily living in the next state distribution. But I didn't yet incorporate the control. Now, what would you do with this?
We project it back to the condition.
What do you do after doing the predict? Now I want to do the update.
Correction.
The correction, yeah. The correction. So, the correction is, first step?
The observation, we have to take care of the observation.
From P, I have P of x of t given t minus 1, right?
Yes.
And then I need to apply the correction. So the first thing that I have to do is, don't worry, you will not, I have a measurement, but I don't know what to do with this measurement. What can I do?
We need to compute the transition.
The transition we have already done with the predict, right?
Okay, so now we need the observation model.
Yes. And what do we do with the observation model?
We mount again. We need other.
We compute
sigma points. The sigma points.
the sigma points we have. We have a family of sigma points here. Right? That's the result of our projection. We need to remember the chain rule. We need to compute P of Z and X. Right? So we need to compute the joint distribution. We have P of A. No? We need to compute the joint distribution in order to, and after we have the joint distribution, then we can slice on the actual point which corresponds to the actual measurement. So, after the predict, I need to use the chain rule, right? Because I start from P of x of t, which is the state distribution before the observation. I have P of z given x, which is basically controlled where the mean changes according to the observation model and the covariance matrix is constant, because I say that it's constant. And then I want to compute the joint P of x and z, right? Which will have the following parameters, mu x, mu z, sigma x, no? Same story. And so like we can use the chain rule actually. But the chain rule, we have seen the chain rule in the unscented space, right? And the chain rule in the unscented space is you take each sigma point of the predicted state. You project each of these sigma points through the prediction function, to the measurement function, and you obtain the sigma points of the measurement you would do if you were in that state. And let's call it Z with I. So you have this family of happy sigma points in the measurement space, And actually you have these larger sigma points, which is consisting of x, so the mean, the state, and the measurement, right? Then you can determine what is the average measurement that you would get by calculating the average of all the measurements, all the sigma points of the measurement. And then you can calculate the cross correlations as we have seen in the unscented chain rule. And after that, I have a joint distribution. Not only I have a joint distribution, I have a joint distribution in Gaussian, in covariance matrix form. And then at this point I can do the conditioning, and to do the conditioning I set the bar, I start from the joint, and I slice it at the point of the measurement. And this is basically the conditioning on the Gaussian that we have seen plenty of times with Kalman. And this gives us the full mechanics of the unscented Kalman filter. So we will have to do a domain switch a couple of times. One time, basically only, because the other one will come for free. The first time will be when we calculate when we need to calculate the prediction state. Because in the prediction we have this initial state, we take this initial state, we take the control, we have to determine the sigma points, we project the sigma points through the transition function, and we have this family of sigma points. With those we can construct apply the chain rule and calculate the joint distribution between measurement and space, but that will come already in covariance form. And then after this is coming, I can do a conditioning, and then I can obtain my state, my updated state. And this is a fantastic slide, colorful and beautiful, that we did with much love, that describes the UKF. This is the story of the UKF. We start from a joint distribution between the previous state and the control that has this form. We calculate the sigma points and we obtain this family of sigma points. At this point, we apply the transition, and we obtain a new family of sigma points starting from the input sigma points, which are the unscented points in the next state. And then we can calculate the sigma points and the mean of the measurement, because we take each of those and we project them through the measurement function. And then we get this tiny little Zi that I'm happy about, which is my little tiny predicted measurement. And now after this, I have a family of predicted measurements. I compute the mean. After I have the mean, I keep on these little tiny sigma points of Z, and I can compute both the cross correlation of the joint and the correlation of the joints, the covariance matrix of Z, which is the part of the covariance, the contribution to the covariance matrix of Z in the joint distribution, which is coming out from the noise in the state, right, which is sigma ZZ. After doing this, I can construct, there's an error here. It's a horrible error, because here we are missing the additive term of sigma Z given X. Here there is an error, guys. I will fix this slide. In this element here, what we are missing is a sigma of plus sigma of Z given X. But okay, so I'm proud, but I missed a slide. I missed a block in this slide, and we will put it basically after this lesson, while Tiziano will be streaming on YouTube the exercise. And then after having computed sigma ZZ, then we will obtain, we can obtain the next state by doing conditioning on the remaining distribution. And this bugs me so much that I have to do it on the spot. I am. no, git pull. But bugs me, because otherwise it will be unclear. Oh. Huh? No. Order. Huh? No. Now you understand why it's a pain to try. Ah. Okay. Now you will appreciate why it's a pain to have the slides. No. Z given x and plus. Okay. Okay. I adjusted the slides online for you guys. And then, so I added this term that was misleading before. And then, basically, with this fix-up, this concludes the lesson on the EKF, on the UKF. If you want to know more, these are further details. There's a paper, or there was actually a tutorial of Thomas that I always recommend for those of you that want to know more about Gaussian. And then if you want to know about the Unscented Transform, look this document by Simon Julia. All right, so now I think we can have a small break. If you have questions,